Hello. So today we're going to be talking about an important subject, which is kinetic energy. And this is important whether we're talking about particles or spacecraft. And in terms of classical physics, we tend to think of a non-relativistic version of this equation, which operates at low fractions of the speed of light, where the kinetic energy is equal to 1/2 of the mass times the velocity squared. And we want to understand how this is an approximation to a higher order expansion of terms in the case of relativistic. So for relativistic particles or flight of objects, relativistic meaning travelling close to the speed of light or some large fraction of it, we think of the total energy as being equal to gamma mc squared, where c is the speed of light, and gamma is the Lorentz factor, which is equal to 1 over the square root of 1 minus v squared over c squared, which we can also write as 1 over 1 minus v squared over c squared to the power of 1/2, and we can write that again as 1 minus v squared over c squared to the power of -1/2, using our laws of indices. And so, on the basis of this, the total energy, which is gamma mc squared, can be written as 1 minus v squared over c squared, power of -1/2 mc squared. Now, the total energy of a particle is given by actually two terms. So total energy E is the sum of the kinetic energy plus another term which we will call the rest mass, or the rest energy, where E0 is equal to mc squared. Therefore, the kinetic energy from this equation is given by E minus E0, which is equal to 1 minus v squared over c squared to the power of -1/2 mc squared minus mc squared. Or to write that another way, the kinetic energy is equal to mc squared 1 minus v squared over c squared to the -1/2 minus 1. And this is an important statement that we want to get to. Now, in this expression for the kinetic energy, the term we are interested in expanding is this. This term here, 1 minus v squared over c squared to the power of -1/2. And to do this, we're going to use something called the binomial series. And we're going to do so in v squared over c squared, which we will call x, where x is a small perturbation provided that velocity is a lot less than c, the speed of light. So we're going to need to expand 1 minus v squared over c squared to the minus a half, which becomes 1 minus x to the minus a half, where n is equal to minus a half. So this is the same as saying 1 minus x to the n. Now in binomial series, there are two versions we can think of. There is the case of 1 plus x to the n, where the binomial series expands approximately to 1 plus nx plus n minus 1 over 2 factorial x squared plus n minus 1 n minus 2 divided by 3 factorial x cubed, etc. And then there's the version which we're going to use, which is the case for 1 minus x to the n, which is equal to 1 minus nx plus n minus 1 over 2 factorial x squared minus n minus 1 n minus 2 divided by 3 factorial x cubed, etc. We could have kept going to higher order expansions, but this is just to fourth order. So we then look at our expansion of terms, and remember the actual term we're expanding is 1 minus x to the minus a half, which is approximately equal to 1 minus a half of x plus minus a half minus 1 divided by 2 factorial x squared minus a half minus 1 minus a half minus 2 all over 3 factorial x cubed, which is given by 1, 2 negatives make a positive, so 1 plus a half of x plus 1 half times by 3 over 2 all divided by 2 x squared plus 1 half of minus 3 over 2 minus 5 over 2 all divided by 6 x cubed. And then we work this out. It comes out as 1 plus half of x plus 3 over 8 of x squared plus 15 over 16 of x cubed. And remember that x is equal to v squared over c squared, and so 1 minus v squared over c squared, so minus a half, is approximately equal to 1 plus a half of v squared over c squared plus 3 over 8 of v squared over c squared all squared plus 5 over 16 of v squared over c squared all cubed. Which is then 1 minus v squared over c squared to the minus a half is approximately equal to 1 plus a half v squared over c squared plus 3 over 8 v to the fourth over c to the fourth plus 5 over 16 v to the 6 over c to the 6. And remember earlier that we showed that the kinetic energy is given by mc squared 1 minus v squared over c squared to the minus a half minus 1. And so we need to substitute the expansion into this equation. And so it becomes equal to mc squared 1 plus a half v squared over c squared plus 3 over 8 v to the fourth over c to the fourth plus 5 over 16 v to the 6 over c to the 6 minus 1. And we see that both of the ones go, they cancel each other out. And so now we've got, opening up the bracket, 1/2 mc squared v squared over c squared plus 3 over 8 mc squared v to the fourth over c to the fourth plus 5 over 16 mc squared v to the 6 over c to the 6. And we can see from this that the c squareds will cancel here, this c squared will cancel here, this will turn into a 2, this c squared will cancel here, this will turn into a 4, and so we end up with a result that the kinetic energy is given by 1/2 mv squared plus 3 over 8 of m v to the fourth over z c to the squared plus 5 over 16 m v to the 6 over c to the fourth. And this is our equation for the kinetic energy, and this is expanded, so there would be in principle higher order terms. We've only gone to a fourth order expansion, and we have the binomial expansion of the kinetic energy. The first term cancelled out because it was 1, and we end up with the second term, the third term and the fourth term. And we note that the first term is simply kinetic energy is equal to 1/2 mv squared, which is the classical description. So let's just understand what this means a little bit. Let's draw a graph of the kinetic energy, which might be in joules, and we're going to plot that as a function of the velocity with respect to the speed of light. So this might be 0 here, this might be 1/2 of c, and this would be 1c. And what we find is for the exact solution, it looks something like this, and then begins to asymptote at c. If you forgive the squiggly line, not easy to draw these plots in this software. And the approximations to the term are accurate except at high relativistic numbers. So, for example, if we only had the first term in the approximation of the series, we might get something like this before it starts to asymptote. And if we only had the second term, it might be something like this. The third order term, and it gets closer and closer to the approximation. And this is the exact solution, say. This is V over C. And so at V a lot less than C, we have the classical description for the kinetic energy, which is that K is equal to half mv squared, and that's okay to use that whether you're looking at particles or even spacecraft. So if you wanted to know the energy it takes to drive a spacecraft at a particular velocity, you can approximate it from the kinetic energy, provided you're looking at low fractions of velocity. But once you start to approach the speed of light, you then have to think about relativistic considerations, and to also remember that the total energy is equal to the rest energy as well as the kinetic energy. And this is important to understand. That's it.